Hello and welcome. In this video, we're going to take a look at the rate of change of a function. We're going to take a look first of all about what it means for a function to be increasing or decreasing. And then we'll take a look at the net change of a function versus the average rate of change of a function. And all of this kind of leads up to calculus, where in calculus we can start computing the exact rate of change of a function at a precise point. And this is really all important information if you're planning on taking calculus. Get a good sense of what it means for a rate of change of a function. So let's start off with a couple definitions, and they may seem obvious, but definitions for increasing and decreasing on an interval. Okay, and these definitions, they look fairly similar. For increasing, we say a function is increasing over an open interval from a to b. That's not including endpoints, by the way. If f of x1 is less than f of x2. Now, here's the important part. x1 and x2 are between a and b, and x1 is less than x2. Now, exactly the same order here. If a function is decreasing on an interval, f of x1 is greater than f of x2 whenever x1 and x2 are between a and b, with still x1 less than x2. The important order here is that x1, x2 are going from left to right inside this interval. But the y values for increasing are going from smaller to larger for increasing, and going from larger to smaller for decreasing. But we're always talking about increasing or decreasing as we travel towards the positive x-axis. So let's just take a look at a little example. Okay, here I've got a function in blue. It's kind of a bizarre looking function. You can see it has a solid endpoint at -2, and it has what appears to be some sort of behavior around x equals 2 that we would call an asymptote. We'll take a look at asymptotes a little bit more in other videos. You can see that the function is going off the negative infinity. It just drops down off the graph. And we may maybe indicate that there's a break in the function here at x equals 2 with a dotted line. But the dotted line isn't part of the function. And then the function continues upwards, and we see this other endpoint here at 5 is not included. Well, first of all, it might be worthwhile just to take a look at domain here. So before we talk about increasing and decreasing, just thinking about domain here, you can see that 2 and 5 are not included in the domain. So the function's domain goes from -2 to +2 without including +2. And then it once again continues from 2 up to 5, but doesn't include that endpoint. Now we can take a look at parts of that domain where the function is increasing and parts of the domain where the function is decreasing. Let's start off with increasing. Now, an interval where it's increasing means that any two values from left to right in that interval are going to go from a smaller y value to a larger y value. And that is always from left to right. So we should really start with this left-hand endpoint here and travel to the right from there. And you can see that at any 2 points in the first interval here, we are traveling upwards until we reach a value of 2. And when we get to the value up here, the y value of 2 seems to be about the highest point that we can get to. And if we start looking beyond that, we're going to find that as we travel to the right, we end up getting a smaller y value. So our first interval along the x-axis would be from -2 to 0. And we say it's increasing from -2 to 0, but not including 0. The reason there is just 0 gives us the value 2, and we can only say they were increasing up to that point, not increasing at that point. Y is 2 is actually what we will call some sort of maximum value there. Now, it seems like we're going to be traveling to the right beyond 0 and dipping down. But on the other side of the dashed line here at x equals 2, we're going to be increasing once again all the way to 5. But with one little exception right here at x equals 4. At that particular point there, we have what appears to be the function being horizontal. And whenever we've got some point here where it appears that we are not traveling upwards to the right or downwards to the right, but we're just basically horizontal, then we would say it's not increasing nor decreasing at that point. So to be a little more technical, we would say it's increasing from 2 to 4. 4 itself isn't increasing or decreasing, but it certainly is increasing from 4 till 5. And of course, 5 isn't even in the domain, let alone it's not an endpoint that we can include anyways. So endpoints like the -2 and 5 shouldn't be considered to be increasing or decreasing. We want to take a look at x1 and x2 being between certain values. Now, what about decreasing? With decreasing, it's not necessarily that whenever a function is not increasing, a function must be decreasing. A horizontal function is neither increasing nor decreasing. That would just be a constant function. Rather than just thinking about where it's not increasing, let's go back and start from the left-hand point here and travel to the right. We already know it's increasing, and when we get to 2, we can see that we're traveling downwards to the right. So it's definitely decreasing from the interval from 0 to 2. Now, it continues to travel downwards until this dashed line. When it starts to travel upwards to the right, we never see it start decreasing again. So it's only decreasing from 0 to 2. So you can see -2, the value at x here, is neither increasing nor decreasing. At 0, which is neither increasing nor decreasing at the very top. Wherever f itself is undefined, places where x is not in the domain, those can't be increasing or decreasing. And again, anytime we see there's some sort of horizontal behavior of the function, that is also neither increasing nor decreasing. Now, naturally, after we talk about a function increasing or decreasing, we also naturally start thinking about after a function has increased and when it starts decreasing again, shouldn't we get some kind of maximum value? Well, let's talk about the different kinds of minimum and maximum values, and which we just tend to call as extreme values or extrema. Now, we could say one of a couple different things. We might say that f of a is a local minimum. Now, we'd be talking about the y value that would be. That would be a local minimum value of the function. Or we could say that f has a local minimum value at x equals a, and that would be just describing the location of a minimum value. Either way, we would be saying that the y value, f of a, is less than the y values of all points nearby. Just like in a little interval surrounding x equals a, all of the other values are greater than or equal to f of a, which is supposedly the minimum. Now, the same thing goes with the maximum. We could either say that f of a is a local maximum value of the function, or we could say that f has a local maximum value at x equals a, and that would mean that f of a is greater than or equal to f of x for all of the values of x near a. So again, just picking any x in a small interval around a, we're going to find that f of x is less than or equal to f of a, which is the maximum. Now, we also can talk about the absolute maximum and absolute minimum values of a function, and it's pretty much the same, except that instead of talking about something being the biggest value in its little neighborhood, we're going to be talking about the biggest value just overall in the entire domain. So let's write those definitions out too, and then take a look at an example. Okay, now thanks to the beauty of copy and paste here, you can see it's the same definition for absolute extrema with one small change here. An absolute minimum or an absolute minimum value occurs when f of a is less than or equal to f of x for every value of x in the domain, not just in a little neighborhood. And same thing for an absolute maximum value. That happens when x equals a if f of a is greater than or equal to f of x for every value of x in the whole domain of f. Think of it kind of like your favorite hike, and it's up to the top of a mountain, and it's the tallest mountain nearby. That would just be a local maximum because it's just a mountain in your city or maybe your local area. But the absolute maximum would be talking about something like Everest, which is the highest peak on Earth. That would be the absolute maximum elevation of the function that is the topographical map of the world. That would be the absolute maximum. So, there is advantages to just finding local extrema, and an absolute extrema is a local extrema, but it's also a little bit more. It is the biggest value overall. Now let's take a look at a function and see if we can pick out local and absolute extrema. Okay, once again, I've drawn a particularly strange looking function here. Y is a function of x. And you can double check. It is a function because it passes the vertical line test. Now the domain of this function is from 1 to 8, but excluding 7, because I have an open dot there, so that's not actually part of the function. So if I wanted to write the domain of this function would be from including 1 all the way up to 7, not including 7. And then from 7 to 8, including 8, but not including 7. Now it's time to look for local minima. And it's probably best to actually give both the x and y coordinates so that we can see the location of the minimum, and we can also figure out the minimum value. Now we are decreasing until we get to 2, and you can see that if I were to take a little interval on either side of 2, 2 would definitely be the smallest value. So I'll put a little point here, and that would be at the coordinates 2, 1. We have a local minimum at 2, 1. And then we're going to be increasing. And of course, none of the values while we're increasing can potentially be local minimum. If you pick any point where we're increasing, going a little bit to the left is lower. So it can't be a minimum. Going a little to the right is higher. So it can't be a maximum. Any place where you already see that the function is increasing, don't worry about looking for a local min or a local max. We stop increasing when we get to the top here at 3, 5. But that is definitely higher than everything else. So we'll keep going. Our next local minimum could happen right here at the coordinates 4, 2. That's going to be another local minimum. And then we are traveling upwards to this hole and traveling back down. And don't forget that an endpoint could be a local minimum. It certainly is the lowest point anywhere nearby. So we have another local minimum at 8, 1. Now looking at the y coordinates of those 3 local minimum, our absolute minimum value seems to be whenever we have a y value of 1. And there are 2 different places where we reach this absolute minimum. We can have 2 absolute minimum values whenever there's a tie. So our absolute, or ABS for short, absolute minimum values here are going to occur in 2 locations, 2, 1 and 8, 1. Now it's time to look for maximum values. Local maximum values are going to be wherever we're at the highest point nearby. Well, starting at the coordinates 1, 3, we already have a place that seems to be the highest value nearby. Traveling either direction, either we're traveling out of the domain, which we can't do, or we're traveling downwards. So that is a local maximum value at 1, 3. Wherever we're decreasing, we can't get a local max. We've already got a local min, and then we're traveling upwards again, which tells us, great, we're going to reach this local maximum here as well at 3, 5. Traveling down to a local min, traveling backwards up, we end up getting to this open circle, and that causes us a bit of a problem. Not in the domain. So we can't have a local maximum at 7. Can we have a local maximum at 6.9 then? Well, that wouldn't be quite as high up as a local maximum at 6.99, which would be a little higher. But that couldn't be a local maximum because 6.999 gives us an even higher y value. And you can continue doing this forever. This would just be a recursive cyclical argument. Every time you pick a number close to 7, you realize that it's not the highest value because you can still get a bit closer to 7. And that's just the nature of the real number line. There's infinitely many numbers between 6 and 7. You can get infinitely close to 7 just by including more decimal places. And that means that since we can never choose a value on the x-axis that gives us a local maximum, we can't actually have one that exists. So there really are only two local maximum values, and there is no local maximum value at x equals 7. It's a bit confusing. It looks like the highest place on the graph, but the point that would have been the highest has been removed, meaning that we cannot have any other point nearby be the highest anymore. Luckily, we do have an absolute maximum. Between the 2 points where we have local maximum values, one is definitely higher, and that'll be at the point 3, 5. Now it's worthwhile noting that when we have a function like we looked at earlier with some sort of behavior where the function dives off the graph and heads down off the graph straight down, we are also not going to get a local minimum here because the function can be made as low as you like, but it never reaches a lowest value. So there's a couple tricky places where we can actually have functions that don't have local or even absolute extreme values. Now that we've taken a look at increasing, decreasing, and extreme values, let's take a look at what it means to have a rate of change. How fast is a function increasing? Or how fast is a function decreasing? And before we talk about the average rate of change of a function, we just quickly need to discuss the net change of a function. The net change of a function f over a closed interval from a to b is simply given by f of b minus f of a. And remember, the function evaluated at b is what we would treat as the y-coordinate. And the function evaluated at a would also be the y-coordinate. So we're really subtracting the vertical positions of a function on a graph over a horizontal interval. So let's take a look at a picture. Okay, here we have a function y is a function of x. And you can see that the domain of our function is from 1 to 5. We can take a look at the net change of this function over various different intervals. And so let's start off with the net change from the interval 1 to 3. Now we can think about this formula as essentially a final y-coordinate minus an initial y-coordinate on a graph. We've got the point at 1, 5, and we've got a point at 3, 25. So when we subtract f of 3 minus f of 1, we are simply subtracting the y-coordinates, which give 25 minus 5 for a net change of 20 units. Well, what about the net change from 3 to 5? The net change from 3 to 5, once again, we're going to be subtracting final minus initial, f of 5 minus f of 3. Now we have the point at 3, 25, and we have a point at 5, 20. Final minus initial, though, we have to subtract 20 minus 25, and that leaves us with negative 5. Remember, we're really only looking at the difference in the y values. For part A, we are simply taking the difference between the current value at 5 and seeing how much of a difference we end up with to our final value. And then the net change from 3 to 5, we will just be taking a look at the difference from 25 down to 20, and that is 5 units down. So we have a positive net change when our final position is higher, and we have a negative net change when our final position is lower. Now notice what happens if we wanted to find the net change over the interval from 1 to 5. F of 5 minus f of 1, final minus initial, that'll be a final coordinate of y equals 20, and an initial coordinate y equals 5, which ends up being 15. And notice what happens. That is precisely the net change from 1 to 3 plus the net change from 3 to 5. This is essentially what is displacement of an object as opposed to distance. Displacement, we're really just figuring out how far away from our initial starting point we started with. We went with 20 units up, and even though we took a meandering path down where x equals 4 and then back up, we only ended up 5 units below where we started at x equals 3. 20 units up, 5 units down, means that from start to finish, from x equals 1 to x equals 5, that means we've only gone 15 units up net change. Okay, now that we've talked about net change over an interval, Now we can start to take a look at the average rate of change over that interval. And what we have is the net change, FB minus FA. That's the difference essentially in the position of the function, the value of the function, or the y-coordinate of the function. And we divide that by the width of the interval, which is just b minus a, since we're traveling left to right in that interval from a to b. So it's just final minus the initial position divided by the difference from a to b horizontally. We can look at this graphically, and this formula is actually one we've seen before, just perhaps not using function notation. Okay, here I've got a function. It doesn't look like it has any particularly bizarre behaviors. We want to find the average rate of change of this function over the interval from a to b. So I've put that interval here along the x-axis. And remember that the point when x equals a is the point a comma f of a. F of a is our y-coordinate. And again, when x equals b, that means that the function has the coordinates b comma f of b, where f of b is the y-coordinate. Now we already see that fb minus fa is the net change. So we can see that the net change is, in this function, going to be positive. And b minus a is simply the width of this interval. And if we take some sort of change vertically divided by this change horizontally, well, we've done that before. That is rise over run. And that is essentially just the slope of a line connecting those 2 points. So if we were to connect these 2 points here with a line segment, we could continue that line segment even off further if we wanted. We would just call that a secant line. And a secant line is a line that connects 2 points on the same function. Now we can see that the slope of that line is also the same formula as average rate of change. Okay, well, let's do another example of a function here with some values along the x and y axis, and we can compute net change and average rate of change. All right, in this example, we've got a function s, which is a function of t. And if you take a look at the axes here, s we have measured in meters, and t we have measured in seconds. So we actually have something maybe of the form of a position being a function of time. All right, well, let's look at the net change over the interval from 1 to 4. You can highlight those points here at 1 and 4. Those will be the interval for time. The net change is just going to be taking a look at the net change in s over that interval, s being some sort of position. And you can see that from the first to the second point here, our position is decreasing. And we only have to look at the net change. We don't have to look at the fact that we've gone up and then back down. We are just going to be looking at the net change of s from 1 to 4. Net change is f of 4 minus f of 1, which at 4, we see s is equal to 8 meters. And the initial position here would be 12 meters. And we don't have to put the units into the equation, but we should definitely put them into our final answer. 8 minus 4 is negative 4 meters. And if you want to think about that in terms of more of a physics terminology, that would be a displacement, because we can talk about a change in position being in a direction, either positive or negative. And this seems to be a change of position in the negative direction. So a displacement of 4 meters in the negative direction. What about the average rate of change? Well, remember, average rate of change is the slope of a secant line connecting those 2 points. So we can connect the 2 lines here and take a look at the slope of this secant line connecting the 2. Now we have rise over run. The formula here would be final position minus initial divided by the change in time, 4 minus 1. And if you haven't noticed already, this is much like just y2 minus y1 over x2 minus x1, which is how we calculate the slope of a line between 2 points on the line. So it's the same formula, but just using function notation. Now, it's probably good to also remember units here, and even if you don't include them in your calculation, you will need to use them in the final answer. F of 4 minus f of 1, we just calculated that's the net change. That's a change of 4 meters in the negative direction. But along the horizontal axis, 4 minus 1. Well, this is in seconds here. 4 seconds minus 1 second is 3 seconds. And that leaves us with a slope, or in the case of an application here, that would be velocity, meters per second. A velocity of negative 4/3 meters per second. And that means that even though we were traveling upwards, you can see we'd have increasing and then decreasing. We're not necessarily able at this point in time to figure out how fast this particle or this object is traveling in meters per second at every point on the curve. But what we can do is we can take an average by looking at two different points and finding the net change divided by the interval width. So I hope that kind of gives you a little bit of an idea. Anytime we have a graph, we can determine when it's increasing and decreasing quite quickly. If you have the actual equation for the function, we can still calculate average rate of change though. Given any function and its expression, you can then plug in numbers and you can calculate the actual average rate of change. It's useful to see this both in a graphical application or doing this computationally. Now, a lot of functions, if they are kind of interesting functions like polynomials, they don't have the same rate of change all the time. They're going to be increasing, they'll be decreasing, so on. However, a linear function is a great example of a function that always has the same rate of change. We call it the slope of that line. And a linear function has a constant slope. That means its average rate of change is always the same as the slope of the line. And we'll be dealing with linear functions frequently. They're just kind of boring. I don't know. I like to talk about things that are, a little more interesting, and then we can talk about where a function is increasing or decreasing. And it can change rapidly depending on the behavior of the function. Anyway, that's it for this video. Thanks for watching. I'll see you again in the next video.